using today is we're doing the washer method. This is not the generation of a surface. There is a whole different problem. Surface area is something you will handle in Calc 2, or actually 3-dimensional. You'll handle it in Calc 3. That's where you figure out surface area of objects, which is really cool to think that you can not just find the volume, which is what we're doing in here, but there are ways of finding the surface area of objects like this as well, which is really cool. I mean, some of the applications you get into, particularly in multivariable calculus, is really actually kind of fun. I think multivariable calculus is actually easier. Most people agree that third semester of calculus is actually easier than the second semester. First and third are easier than the second one because there's some nasty stuff you'll get next year that we just don't get into. Sorry, just like, okay. Washer method. To find the volume of solid revolution using the washer method. So, the disk won't work. Slicing won't work. That's what the washer method does. The washer method covers when disk won't work, when slicing won't work. So, first thing we need to discuss, choose the correct formula to find the area of the annulus, and that is the technical term, flow. So it's hard to read. Big R is the outer radius, little r is the inner radius, and which one is the correct one? A, B, or C? Which one? B. Big R squared times pi, little r squared times pi. Because this is what we're dealing with today. Instead of a disk, we're dealing with this formula here. So consider the volume of solid revolution. Consider the region enclosed by the curves y equals x plus 4 and y equals x squared plus 2. So I have an example. I have it there. Is rotated about the x-axis. So our axis of rotation, the x-axis there. Can we use the disk method on this? You can't, because for the disk method to work, it has to be a solid disk for your cross sections that you slice it into. The boundary of rotation, the axis of rotation and the boundary of your object have to be the same to use disks. I can't use disks on this. This is the washer method. We will come back to this in a little bit because we're actually going to figure out that volume. Okay. So what would that solid look like? Yeah, it looked like that, kind of like a cone with the inside to be curved. So you have a nice little curve on the inside cone. There are reasons for that kind of stuff. It may look like it, but nozzles of like rocket engines are not straight line nozzles and cones. They've got curves on the outside, curves on the inside as well. They have to get that combustion chamber in there, and they've got to get it right the whole 9 yards. Okay. In our disk method, we set up a single rectangle in the region perpendicular to the line of rotation. Okay. Same thing we did when we did solids. When we did disks, not washers. We set it up. We found our radius. We took a rectangle and found it out. You do the same thing here. I have this is x squared plus 2 and x plus 4. This is what we're rotating around. It will have a matching part down here. Let's see, it's hard to sketch these sometimes. Okay, but there'd be the cross-sectional area of what I'm talking about. Yeah, it's actually not bad. Not great, but not bad. As we rotate around, if we were sliced down the middle of that object, that's what we would get. Okay. So we have a rectangle here. We spin it around. What do we get? We get a washer out of it. Oh, wow. Same idea. We want to add up an infinite number of very, very thin washers. How do we do that? Cross-sectional slice times an infinite number across. How do we add up an infinite number of things? We do an integral. Okay. So that's what the shape looks like. So the formula for the washer is, okay. So for that washer, for that one individual piece that we get, the volume of that one individual piece is pi big R squared times the height, or the width in this case, minus pi r squared, little r squared, times the height. But our height is actually the width. If we go back and look at the diagram, okay, our height is this width here. Big R squared, little r squared. Our height is this width here. What is that? That's delta x. That's our change in x. That's our difference between one x and the next x coordinate we have. That's our delta x. If we take that h and factor it out, this is what we get. This is the formula you need to have. Factor out the pi in front, factor out the h. The h is our dx. So it's really not terribly difficult. And that pi can be either inside or outside. That pi is when we start doing AP work. It says 1 point for the balance and constant of integration. That pi is the constant of integration they're talking about. So if you don't include that pi, you lose a point right off the bat. Just saying. But that's what when they say 1 point for that, 1 point for the upper bound, lower bound, and the pi. And it can be either in front or inside. It doesn't matter. I think they always have an outside in their answer, but really, as long as you have pi as part of it, you're okay. I like to pull it out because it tends to make it easier to do the work. Without pi involved in typing it into your calculator, or if you're doing it by hand, pull the pi out in front, get it out of the way, do the integral, and then slap pi on your answer. I like that. It makes it easier. Okay. So let's go back and let's do the problem that we were talking about. Okay. So we have x squared plus 2 crossed by the line y equals x plus 4. And we want to revolve that around, and we want to figure out what that volume is. So we have the formula, okay, the integral from a to b of pi r squared, or sorry, pi times big R squared minus little r squared. So I need to find the bounds where they cross. I need to find this point and this point, or at least the x coordinates. I do that by setting them equal to each other. X squared plus 2 is equal to x plus 4. So I get them all on one side. I get x squared minus x minus 2 is equal to 0. Negative 2 and positive 1, so I get 2 and 1. 2 and negative 1 is what I get from that. Right? Am I good? Is my algebra good? I should hope so, because I'm doing a lot of factoring in algebra too. I should be getting really good at this. Okay. So you have to have your bounds. And then you have to figure out what's your big R and your little r. Once again, this is the most difficult part. This one's not so bad because our axis of rotation is the x-axis. But you need to find big R and little r. Now, when I do this, I do it on tests, do it on quizzes. When I make an answer key, that's what I have for my drawing. I do want to know the relationship between the axis of rotation, whether it's above or below the things I'm rotating about, and where the relationships are. So I need to know where the curves are, and in relationship to the axis of rotation, whatever line that may be. And it varies depending on whatever line that may be. And I need to find big R and little r. Now, the nice thing about this one is that because our axis of rotation is the x-axis, big R and little r are just the equations. So big R in this case is x plus 4. Little r in this case is x squared plus 2. And that's easy because the x-axis is our axis of rotation. The distance between the x-axis and the function is that function. And whether it's negative or positive, it doesn't matter. It is that function. That's the distance. Right. So my volume is equal to pi times the integral from negative 1 to 2 of big R squared, x plus 4 quantity squared, minus little r squared, x squared plus 2 squared dx. And that's our equation. Type it in your calculator, square it out, combine up like terms, take antiderivative, however you want to solve it. I don't care. In fact, I'm not working out the answer right now anyway, because what's more important? The setup. From here, there are several ways to solve this one. I'm not worried about solving it today. I'm worried about the setup, because that's the hardest thing to do is set it up. Okay? Yes.
So is R anywhere between the
axis of rotation and the object I'm rotating, the edges of the object I'm rotating. So the axis of rotation on this one is the x-axis. So if I'm spinning around the x-axis, this is the center. To get from the center to the outside edge, center to the inside edge. Okay? Does that make sense? Any questions about this? Because understanding big R and little r and finding big R and little r is the most difficult part. The intersections, where your upper and lower bounds come from, we've done that lots of times. That's not new. Oh, where do they cross each other? I don't think that's the difficult part. It can be if the equations are nasty. But if the equations aren't nasty, finding out where they cross each other is not a big deal. Understanding how to find the big radius and the little radius, that's the hard part. Okay. Questions? Anything?
What if the thing we rotated around was like y equals -4?
We're going to get to that. I'll give you an
What do you used to like?
I'll give you an example where it's offset, where it's off the axis.
Just like minus 5.
You add or subtract depending upon where you're at. You add or subtract depending upon where you're at. And then we will have at least one example of that that shows you how to do it. Okay. Number 2, find the volume of solid generated by rotating the region bounded by y equals the square root of x and y equals x squared about the y-axis. So you get this funky little bowl-shaped thing. So here's what I want you to do. Draw the diagram. Label on the diagram big R and little r. Read the question carefully, because that will tell you how you need to do this. So I want you to take a minute. Don't worry about setting up the integral yet. First things first, draw the diagram, and on that diagram, figure out what big R is and little r. And remember, don't draw these teeny tiny little diagrams that are only about that big on your paper, because nobody can freaking read them. You do it on my quiz and test, your diagram needs to be big enough I can see what you wrote. Okay, so let's do the setup on this one. So I have x-axis, y-axis, square root of x, x squared. Y equals square root of x, y equals x squared. My points of intersection, the origin, and the point 1, 1, which is really kind of nice. Okay, makes it easy. Nice equations to work with. What am I rotating about? I'm rotating it about the y-axis. This is my axis of rotation right here. I'm spinning it this way, which means my radii go out in this direction here. Little r, big R are that, and I can't do it because I'm doing it y. My axis of rotation is along the y-axis. This means I have to do it dy, not dx. So what I need to do is I need to convert both of those. If y equals the square root of x equals y squared. And if y equals x squared, x equals the square root of y. It's actually kind of nice. But which one's which? That's the important thing. So my big R and my little r. My big R would be square root of y, because it's this curve here is my big R. And if y equals x squared, that means x equals the square root of y. So this is the square root of y, and r would equal y squared. Okay. That's what you're doing, because this is the curve, this curve right here, that's y squared. That's what my little r is that distance from the y-axis. Axis of rotation is an axis, so that's what I do it on. And this is my big R. It goes all the way out to this equation here, which is x is equal to the square root of y. So that's why my big R is square root, little r is y squared. So my volume is pi times integral from 0 to 1 of the square root of y squared minus y squared squared. Yes. Oh, wait, not dy. Where do they cross each other? Where is y equals the square root of x? Where is y equals x squared? Where are they equal to each other? So set the square root of x equal to x. It's going to happen at 0 and 1. Okay, so that's where my bounds come from. Where do they cross each other? At the point 0, 0 and the point 1, 1. So it actually makes it nice for both of those. Okay. And this would be an easy one to do by hand. Square root of y, the square root of y squared is y. So you get y minus y to the fourth. That would be a very easy one to do by hand. Take the antiderivatives of both of those. Plug in 1, because when you plug in 0, it's 0. So it's actually not that hard. I think it ends up being 1/2 minus 1/5 times pi. Yeah.
Yeah.
So that's not that hard to do. Okay. Find the volume of the solid of revolution generated by the region bounded by, the same ones. Oh, that should be, sorry, y equals the square root of x and y equals x, rotated about the line, x equals 2.
No.
Draw a picture. Leave room to write on your picture, including drawing the line of the axis of rotation. Okay. So I'm going to give myself a little more room here. So there are my two curves, approximately. Y equals x, y equals the square root of x, where they cross at 1 and at 0, so 0.1, 1, and 0, 0. Our boundary of rotation is the line x equals 2. So there's 1. So I'm actually going to erase these to get them out of the way. There's my boundary of rotation. Okay. So my big R, my little r, they come from the axis of rotation. It's important you draw the diagram and you draw the axis of rotation, and then you draw your radii. I go from my axis of rotation until I hit the first curve. I go from the axis of rotation until I hit the second curve. You have to draw this in. If you're trying to figure it in your head, you draw this, it's easy to picture. Okay, here's my little r. Here's my big R. Accordingly. Now, the equations, on the other hand, so looking at the big R, I need to take this, and this is y equals the square root of x. So because I am rotating it this way, I have to do it dy. So my equation would be, this distance here would be my equation. X equals y squared. If y equals the square root of x, x equals y squared. That's my length. Big R is not that equation. Big R is the distance from here to here minus the distance from here to the curve. So this is y squared That's big R. Those two together give me what? They give me 2. So my big radius is 2 minus y squared. That's my big R. Because I go all the way out to 2 and then I come back to where the curve is. The entire distance from the y-axis to the axis of rotation is 2 units. R is those 2 units minus the equation y squared. Little r does the same thing. 2 units and then back the equation. So 2 units over, this equation is y equals x. So that's x. So little r is 2 minus x. 2 minus x gives me my little radius. So little r is 2 minus x. Sorry, 2 minus y. My bad. 2 minus y. Thank you. 2 minus y. Well, it is technically x as well because x and y are equal.
Yeah,
Technically. But that would be bad. Okay. It's important. It's important if your axis of rotation is off the center to make these appropriate adjustments. So my integral would be for my volume would be pi 1, 1. That's where it's at because it's still dy, but what is the axis? Is 1, 1. That's where they meet. So it'd be from 0 to 1 of big R squared 2 minus y squared squared minus 2 minus y squared dy. This is a, without the answer, 3-point problem. If not 4. Usually, and this is what AP does, this is kind of what I'll be doing, is this is worth 2 to 3 points, minus 1 for each mistake. Forgetting to square is a mistake. Not having the adjustment of the 2 is a mistake. Having these 2 backwards is a mistake. So, you know, literally on the AP, and we'll see it when we look at them, you'll see, ooh, 2 points for the integrand, minus 1 for each error. And you'll get 0 points. And if you get 0 points because you made a lot of mistakes, they don't bother to figure out what your answer is based on your wrong bounds. Your bounds are wrong. A lot of times what they'll do is they'll figure out the integral. If there's a mistake, they'll still figure out the integral and see if you got the right answer for your wrong equation. But if your wrong equation is so wrong, they'll say at some point, screw it, you're so far off, we're not even going to look at that part. If you make a minor mistake, they will do it. If you make a major mistake, they won't. Okay? That's actually kind of nice of them to be able to say, okay, well, you got the wrong equation, but you're close enough. We're going to figure out what the answer should be based upon your mistake. And if you get the right integral for your the right answer for your wrong integral, it will sometimes still give points. Okay. As another one I do want to talk about, let's consider the same setup. But what if my axis of rotation was -2 on the y-axis? Okay. What if this is my axis of rotation? Then this would be little r. This would be big R. And it would be 2 plus what the equation is. Because this distance here is 2. That's 2. This is the first equation. That's the second equation. So it would be 2 plus each equation. Okay, does that make sense? So it's really important you draw, guys. It's really important to draw a diagram for this and draw where your axis of rotation is to help you find big R, little r. Because make a slight change, you're adding to the equation, not subtracting it from 2. You have to know which is which, and this is the best way. Because finding that radii, that's the most difficult part of these equations. Once you get those, it's really not that bad. But figuring out what that's supposed to be, that's the hard part. Okay.